record. We're live on the internet. Welcome everybody, and we have a couple of homework questions in section 3.3 part 1. And I lost the chat, but I believe it was questions 7 and 10. Yeah, 7 and 10. All right, so let's take a peek, see what we got. Number 7. Okay, yeah, so we did a problem like this at the end of class yesterday. So we have this position function, and S is the typical variable for position, which comes from physics and Latin. And it's a function of time. And let's do it. Screenshot. All right. So V is velocity, and velocity is change in position. And so what we need to find first is the derivative with respect to time of our position function S. So that's the derivative with respect to time of our function 2t cubed plus 5t plus 9. And we're moving beyond the difference quotient here, so we're going to do the shortcut rules instead. So shortcut here for the derivative is we have the power rule that says bring the power down and then reduce the power by 1. So 3 times 2 is 6, and that's going to be a t squared. Power here is 1. 1 times 5 is 5. Reducing that power by 1 gives me t to the 0, and a variable to the 0 power is 1. 1 times 5 is still 5. And then the derivative of 9 is 0, and so this right here is my velocity function, given the position function. And then we want to know what's the velocity at 3 seconds. And so that next part right there, so this is part A. Part B is simply what is V evaluated at 3, which is just 6 times 3 squared plus 5. So what's that? 6 times 9 plus 5. On a good day, that's 54 plus 5 should be 59 for my version. So up here, I have 6t squared plus 5 as the function. And again, we took the derivative of position with respect to time, and we're being told that that's measured in meters per second. So position is in meters here, and time is in seconds here. So now we have, this is at 3 seconds, this thing is moving at 59 meters per second, so it's moving in a positive direction there. Acceleration is the derivative of velocity, so it's the rate of change of velocity. So if we find the rate of change of our velocity function, which by the way is the rate of change of the rate of change of position, what we're looking at is the second derivative, which is written like this, of position, and that's acceleration. And there's another video of this from yesterday's class in the playlist. So this is part C. So the derivative of velocity, switch color, find the derivative of 6t squared. Power rule says 2 times 6 is 12. Reduce the power by 1, so that's t to the first, or just t. Derivative of a constant is 0, so I'm done. That's it right there. And then evaluating that at 3 seconds, so the acceleration at 3 seconds is just 12 times 3. And let's see, what is 12 times 3 on a good day? It's 36. And I mentioned the other day is we divided by t again. So acceleration is measured in meters per second. Velocity is measured in meters per second, but then we just divided by time again, so we divided by seconds again. So I prefer the units meters per second, but often physics people rewrite that as meters per second squared, which is the way it's shown here. So all that is the rate of change of speed, which is we call acceleration. So the acceleration here is 36 meters per second. And that's that. All right, so further questions on this one? So this is homework 3.3, part 1, number 7. All right, hear no voice, chat's quiet, so I'm going to move on to number 10. Number 10, the graph of f of x equals 2x cubed plus 3x squared minus 120x plus 6 has two horizontal tangents. So we talked about horizontal tangents a few times now. If we have a horizontal line, the slope is 0. One occurs at a negative value of x, the other occurs at a positive value of x. What is the negative value of x the horizontal tangent occurs at? So we need to take a look at the derivative, which is the slope function. So let me screenshot this. So I have the right information. All right, so again, we're asked here about horizontal tangents. And horizontal tangent means that the slope is 0. Okay, so horizontal line, slope is 0. F prime of x, the derivative, is a slope function for the original curve. It tells us the slope at any point. So we need to find the slope function and see when it is 0. So if we take the derivative with respect to x of our 2x cubed plus 3x squared minus 120x plus 6, what do we get? Well, the power rule, bring the 3 down. 3 times 2 is 6. Reduce the power by 1, that's a 2. Plus, bring the power down. 3 times 2 is 6. Reduce that power by 1. So it's x to the first, or x. Here the power is 1. 1 times 120 is 120, and we're subtracting there. And then x to the power 0, right? Reduce that power by 1. X to the power 0 is 1. Other way to think about this part right here is that just that chunk right there is a line, and that line would have a slope of negative 120, which is what I wrote right there. And then plus 6, constant, derivative of a constant is 0, so I'm not even going to write that. So this is my slope function here, f prime of x. And I want to know when the function has a horizontal tangent, which means the slope function is 0. So then we set this equal to 0 and solve. Let's see, easiest way to solve this is probably factors, and I can see that 6 divides every term here. So if I divide everything by 6, 6 goes into 6 once, so I get an x squared. 6 goes into 6 once, so I get a plus x. And 6 goes into 120 20 times, and that's a minus. And then, let's see, I need factors of 20 that give me a difference of 1, so that'd be 4 and 5. So this would be x times x gives me x squared. 4 times 5 gives me 20. And if I want a positive in the middle, the 5 has to be positive and the 4 has to be negative. So that gives me x minus 4 equals 0. Adding 4 to the other side, I get x equals 4 is one place we have a horizontal tangent. And then x plus 5 equals 0, so x equals negative 5 should be the other place, but we really should check. And since we have such powerful graphing tools easily at our disposal, let's throw this into GeoGebra or Desmos to check that that is indeed where horizontal tangents happen. I'm going to use GeoGebra, which is my favorite, but if you like Desmos, same things apply there. All right, so my function f of x is equal to 2x raised to the third power plus 3x raised to the second power minus 120x plus 6. Take a look. Plus 6. Okay, I think I typed that correctly. Yeah, and then we need to change the scale here. So that's one reason I like GeoGebra. I can just go to the tools, move graphics, and then I can grab the y-axis here and rescale it by dragging. And I'm looking for a place where there's a horizontal tangent. All right, So the tangent over here would be negative. The tangent here is positive. So at the bottom, there should be a 0 tangent there. And if I graph the line, x equals 4, that looks like it is the bottom there. So there should be a horizontal tangent there. And then if I graph the other one, x equals -5, yeah, that looks like the top right there. And to double check, I can plug in my slope function, which I like to call d of x for derivative. And my derivative function was, let's see, 6x squared plus 6x minus 120. And I can see my derivative function has zeros at -5 and 4. And so just to double check, I can ask, what is the derivative at x equals 4? And GeoGebra says, yeah, it's 0. And what is the derivative when x equals, oops, there. What's the derivative when x equals -5? It's 0 there also. So I found the two places where horizontal tangents exist there. Nice. Questions on this one? So we found function has horizontal tangents. X equals 4 and -5. All right, a couple more questions. We got number 12 and number 8. Yeah, nice. Okay, so we got that one. Let's check out number 12 next. Find the derivative, hint, expand it first. So you got to multiply that out. That's it, and then it's not too bad from there. So 7 minus 5x squared. And the only way we have to solve this problem is to square that out, which means you have to take 7 minus 5x times 7 minus 5x. And distributing, we're going to get 7 times 7 is 49, and then we're going to get 7 times 5 is 35, and another 35, 35 and 35 on a good day, I think is 70. And then negative times a negative is a positive 25x squared. So that's my function right there. Now I can take the derivative of it. So the derivative with respect to x of all of that, I'm going to rewrite it as 25x squared minus 70x plus 49 is 2 times 25 is 50x. Derivative of negative 70x is negative 70. Derivative of 49 is 0. So this is my slope function, aka the derivative. All right, what do we want to do with it next? Now find the tangent line to the curve at the point 1, 4. All right, let's do it. Now they give us the point 1, 4, so x is equal to 1. So at the point 1, 4, slope m is just f prime of 1. So that would be 50 times 1 minus 70. And 50 times 1 minus 70 is negative 20. And we really should graph to check that works. So we'll do that in a second. Then we use the point slope formula, y minus y1 equals m times x minus x1, which we used a ton of times over the last few weeks. So that would be y minus 4 equals negative 20 times x minus 1. And they asked us to solve for y here, so no problem. We distribute that, negative 20x plus 20, add the 4 to the other side. So the tangent must be negative 20x plus 24. Maybe, let's graph it and check. So let's get a new version of GeoGebra here. And now I could have made mistakes anywhere, so I'm going to go way back to the beginning where they told me the function was equal to that square. So f of x equals, parentheses, 7 minus 5x raised to the second power. All right, so there's my function right there. And I want to look at the point 1, 4. So I'm just going to verify that's the correct point. I just took their word for it. So 1 comma f of 1. Yep, it is 1, 4. So there's my point. And then I think that the tangent line is y equals negative 20x plus 24. And so then I just need to zoom in there and see if that looks good. Now at first glance, that looks like a tangent line. I'm just going to rescale to double check. So let's expand that way and decrease that way. Yeah, that looks pretty tangent to me. Okay, so the graph matches what I calculated. So in order to use the rules we know so far, we don't have a rule to do this at first glance. We have to multiply it out because yesterday we went over how to work with polynomials, so I have to write it as a standard polynomial. Then I can take the derivative, evaluate, find the tangent line. All right, further questions on that one? Okay, so we're good on number 12. It looks like we're good on number 8, but maybe a question on 16. All right, let's take a peek. But I am curious about number 8 now. Just want to take a quick look. I'm so excited you guys are asking questions. You made my day. Okay, yeah, that's not too bad. That's pretty much like we just did. All right, number 16. Ooh, let's see. Yeah, so we're looking for a growth rate, and remember, derivative is a rate of change function, right? That's what we've been working on all quarter. Rate of change is the derivative, so this just means, hey, take the derivative and plug in 3. So let's bring that to my notebook. New page, please. Okay, so again, we're asked for the growth rate here, and we're given the population function here, where P is the population of the bacteria colony over T hours. So the growth rate then would be the change in population over change in time. And so that means take the derivative of that function right there. Oops. And again, change in population, so this should just be bacteria per hour, because that's what we're calculating here. So the result of that, the units are bacteria per hour. So the power rule says bring the power down, 2 times 5 is 10, reduce that t to the second to a t to the first. Derivative of 24t is just simply 24, and the derivative of 200 is 0, so we just skip it. And then we want to, this I could call also p prime, and I want to know what is p prime at 3, and so I just replace the t with a 3, and so that's going to give me 30 plus 24 for my version, or 54. So 3 hours in, this is growing at 54 bacteria per hour. So it looks like a pretty slow growing bacteria culture. I don't know, how fast do bacteria grow in general? I don't know, but I'm assuming that is maybe realistic. All right, cool. Thank you for asking homework questions. Good job.